Hi there guys, this is 14E. We are testing for the mean of a normal distribution. This follows on more from 14B and 14C where we were testing for the binomial distribution and testing for the Poisson distribution when we were using hypothesis testing for those, and we were checking or testing rather to see whether or not P was correct, the probability was correct, the parameter P in our binomial distribution, and lambda or alpha or the mean was correct in the Poisson distribution. Right here, we're testing the mean of a normal distribution. Now, this is going to lead to two tests, and one of them we can do without using the testing facility on the calculator, and we can do it using that as well. So there's going to be two ways of doing the Z test. And for the t-test, there's one way of doing that on your calculator, but we'll deal with z-test in 14E. Okay, so perhaps let's look at one of the questions. So let's look at, skip the investigation. Investigations you can find, by the way, the answers to those from the teacher notes at the start of the chapter. They're hidden. But let's look straight at example 5 here. Okay, so example 5 says a machine fills bags of flour with a labeled weight of 1 kilogram. To make sure the bags are being filled correctly, a sample of 40 is taken and their weights are measured. The sample mean is found to be 995 grams. So we can see this is obviously lower. This is lower than the 1 kilogram that should be in these bags of flour. From past experience, it is known that the standard deviation of the bags filled by the machines is 20 grams. Right, this bit is what tells us we need to do a Z test and not a T test. If they say that we don't know the standard deviation and that we're going to have to estimate the standard deviation from the sample, then we're doing a T test. So T test requires an estimate of the standard deviation. Z test and standard deviation is known. Okay, now T tests are more realistic because generally you don't know what your standard deviation is from before, and we don't know that based on this sample as well. So Z tests are slightly more unrealistic, but in this question they're trying to keep it slightly simpler, and so that's why. And so they're telling us that the standard deviation is known. So therefore we're going to use the Z test. Okay, right, let's take some of that back. Okay, so then in part A it says use the p-value to test whether there is sufficient evidence at the 5% level that the machine is filling the bags to less than the correct weight. Okay, so because we're doing a test here, we need to first of all state what the original distribution is. Then we need to state what our null hypothesis is and our alternative hypothesis. So we're going to say, let's call this potentially X. I think they're saying X in the answers here as well. They haven't actually defined X to be a bag of flour chosen from this set of bags of flours. So X is normally distributed with a mean of 1 kilogram, so 1,000 grams, and a standard deviation of 20. Okay, so standard deviation of 20. Now, this is where your central limit theorem comes in as well, because they're now talking about a mean. So they're talking about taking a sample of 40 in this case. Now, a sample of 40 means that we can use the central limit theorem. Actually, they didn't say that the original distribution was normal. But luckily, our sample is above 40. So this is not necessarily the case. Okay, so that's not necessarily the case, in fact. But because we've got the fact that the sample is of size 40, we can now go from this any distribution to a normal distribution in this case because of the central limit theorem, which we discussed in chapter 13. So we now know that X bar is normally distributed with, and again, according to the null hypothesis, with a mean of 1,000 and a standard deviation of 20. Now that's for one of the bags, but because there's a sample of size 40, the X bars are going to be distributed by, again using the central limit theorem, by 20 divided by, that's 20 squared because we want the variance, 20 squared divided by 40. Now that means, of course, that our standard deviation that we're going to be using here is actually 20 over the square root of 40. Okay, that's just central limit theorem. And we can use it because the sample size is 30 or more. Okay, so for part A, it's saying use the p-value test to see whether or not there's significant evidence. Oh, we haven't written down yet H0. And H0 in this case is that mu is equal to 1,000 grams. All in terms of grams because the standard deviation was in grams. And H1 was that, now this is a one-tailed test because we're testing to see whether or not there's less than the correct weight, not simply that it's filling them up incorrectly. It may be that this machine has started to put too much flour in each of the bags instead. So in this case, though, they only want to test to see whether or not they are lower than the standard. So we're testing to see whether or not mu is less than 1,000. So that's the test. Notice that we are not here saying that mu is equal to 995. We're just seeing if the original distribution, or the fact that the sample distribution should follow this, the sample mean distribution should follow a normal distribution. We're testing to see whether or not this distribution here is incorrect from our sample mean distribution. Okay. Right. Okay. Right. Let's just clear everything out there for a moment, and let's see how they've written it down. So let's just look at this. So again, same thing. H0, mu is equal to 1,000. H1 is mu is less than 1,000, and in this case, again, they've really missed out here, and I really would have put this in. The X bar is normally distributed with 1,000 and comma, what did I say? 20 squared over 40. 20 squared over 40 there. Let's just close that one off. Hard to see me closing off there. Okay, so how are we going to work this one out? We need a p-value for this, and we need to check that the p-value is to see whether that's less than 5% or not. If it's less than 5%, then we will accept the alternative hypothesis. Okay, well, how are we going to do that? We can go to our calculator now, and we can go to calculate, so we can go directly to Scratchpad. So we can go to menu and probability and distributions, and we're looking for normal CDF. A normal CDF where we're talking about a lower bound being minus infinity, if you like, but you can put in some incredibly low number, minus 999, or maybe you can think of numbers which are lower than that. Okay, so, and then the upper bound here is going to be 995. Remember, a normal distribution, you shouldn't start at 0 here because, you know, it could be, even though, of course, this is probably going to go down to 0 extremely quickly on this end, but you should just try and trap as much as possible. It's all this side here. It's not from 0 until this critical value point here. We just want to go all the way back, and that actually goes on infinitely here to the left-hand side. So we're going to go from negative infinity to the upper bound of 995, and we're going to check to see if this is 5% or more, or 5% or less than 5%, right? So we've got mu is equal to 1,000, and I'm going to put standard deviation in as 20 divided by, and I'm just going to write in, so I'm going to put in square root of 40 here and close that one off, and okay on that. So I'm getting out the answer of this here directly from my calculator. Okay, so there we go. That's done. Let's just clear my annotations on that one. So you can see that clearly this is above 5%. therefore, at the 5% level, there is not sufficient evidence to reject the null hypothesis. In other words, we will keep accepting the null hypothesis and reject the alternative proposition here. Okay, so then part B says find the critical region for this test. Now, this is where it comes in useful to be able to draw your sketches, because in this case, we're looking for this critical region. So again, we're talking about this distribution here, and we're talking about mu equaling to 1,000. We've got a standard deviation of, so we've got standard deviation was this was 20 divided by the square root of 40. What's that? Something like 20 divided by 6, something like 4. So roughly, you're going to get 68%. So within one standard deviation of the mean is going to be somewhere between 996 and 1004. I'm making rough estimates there. Okay. So 995 is going to be somewhere over here. And find the critical region for this test. Now, actually, 995 is not important for the critical region of this test. We just want to compare to see if 995 is in that critical region later on. So we need to find now the exact point at which we're trapping in 5% of our probability, or up to 5% of our probability. So we're trying to find this value here. Sorry, it's totally scruffy. Let's get rid of all of this. So we're trying to find this critical value here, R if you want to call it that. So where we're trapping in here are 5%. Now, because the normal distribution is a continuous distribution, we don't have the same issues that we had with the binomial distribution and the Poisson distribution, because there we had an issue of saying, well, look, if we had a bar in this case which overlapped that 5%, if you like, then we would have to start from the value before that bar, because we don't want to trap in anything more than 5%. Now, with a normal distribution, we don't have to worry about that, because we can actually find the continuous value, which gives us this decimal value, which will give us exactly 5% in this region. So in some respects, the normal distribution is easier to use. Okay, so again, I'm going to use my calculator for this one. I'm going to go to Scratchpad, and go to Menu, go to Probability, I'm going to go to Distributions, and then for distributions, I'm going to go Normal CDF. No, I'm not. I'm going to go Inverse Normal. And the area where I want to trap in this case is 0.05. Now, if I was doing this the other way around, if I was doing a test to say whether or not we think that the machine is overfilling the flour bags, then I would want to test 0.95 as our probability there, because we want 5% in this region here. But in this case, we want up to 5%, so it's cumulative probability, but we're going to do the inverse probability, which always gives us the probability before that value. Okay, so in this case, we want 5% there, so an area of 0.05. Mu is equal to 1,000, and again, the standard deviation here is going to be equal to 20 divided by the square root of 40. Just putting that into my calculator now, pressing OK, and that's giving me a value. In this case, our critical value is 994.7985, so on. Okay, so that's what it's giving us. And again, because that's now the critical region is now when our x bar, in fact, in this case, is lower than 994.79, so on. Okay, so that's our critical region. So we found that now. This is the critical region. And is 995 in that critical region? No, it isn't. So therefore, we would reject the alternative hypothesis in this case. Okay, so let's just see how the book's laid that one out, and then let's see how they've done it on the calculator as well. So let's stretch this one out. Critical region. So you can see what they've done here. They've said inverse normal value is, they're putting in 0.05, they're putting in 1,000, they're putting in this standard deviation from the central limit theorem, because we're looking at the distribution of the mean and not of x. And again, we're getting the critical region in this case. Okay, so that is done. We've done it in two different ways there. Okay, well, let's check how the book does it, because they've got an alternative version of this. And so if you click on the little calculator in the corner and you go to the calculator, you open this one up, same question. And we can see here that it tells us here, in this case, to go to statistics and then stats tests. So we're going to go to calculate, to Scratchpad, and then we're going to go to, on the TI Inspire, we're going to go to statistics, and then we're going to go to stats tests. So this is an alternative way of doing it. Now, since we know what the standard deviation is, they tell us the standard deviation, we're not having to make an estimate for it. We're using the Z test and not the T test. Now, we want to go to Z test. That's number one in stats test. So this is a common test, of course. So it's Z test. And we're going to go to the input method of the stats. We have the stats available for this. We're going to go OK on this. Now, we get asked for your mu, so the null hypothesis mu, which is 1,000. We have again that sigma is equal to 20. Now that's kind of interesting. We're not putting in 20 divided by the square root of 40 in this case. And we're not doing that because they're asking us for n later on. So they're just saying, what is, under the null hypothesis, what is the standard deviation? And then our test will be based on a certain n number. So we'll do that part for you. So they'll do the central limit theorem for you in this test version. Okay, so standard deviation is 20. X bar is equal to 995. N is equal to 40. The alternative hypothesis will need to change because we have an idea that this is going to be lower. So we're testing to see whether this new mu is, or new value for the mean is lower than 1,000. So we're doing mu is less than mu 0. And then I'm going to press OK on this one. And it gives us essentially this table here. Okay, so let's zoom right into this table here and discuss that briefly, okay, to see what that means. So what are they giving us from this? So they're telling us what we're doing. We're telling us the alternative hypothesis. They're telling us Z. Now, Z is a normalized statistic here. You do not need to worry about this. But it's basically they've normalized the distribution to make a sigma of 1 and a mu of 0. Okay, but you don't need to worry about this. Then they've got the p-value here, so they're going straight to the p-value. And then they've got the things that you put in, of course. So they've got the x bar, they've got n, and they've got sigma as well. So everything here is just the stuff that you put in. You can ignore z, and then you can go straight to the p-value in this case, which is above 5%. So therefore, we reject the alternative hypothesis. Okay, so that's giving you the p-value version, but it is not giving you the critical region value, which is obviously how I explained to do it on the calculator before, and they show you this afterwards as well on the sheet, of course. Okay, so you don't need to know this Z-test method, but in fact, the Z-test method will only give you, let's just check back to this. So again, if you use the Z-test method, you can only do part A, you cannot do part B. So part B comes about from you understanding the central limit theorem needs to be found out, and that we need to do the inverse normal distribution in this case here. Right, okay. Now, with the t-test later on, we'll only be looking at the p-values. Okay, well, that's a lot of information there. Took a little bit longer than I thought it would. But that's only half of this exercise, because we also need to consider two-tailed tests as well. So what we did here was a one-tailed test. We did a one-tailed test because we're only looking at the probability on one side here, and the null hypothesis was that mu was less than mu0. Okay, so let's look at another type of question here. Let's look at the other way around. So two-tailed tests, if we're going to do a 5% test for a two-tailed test, we'd be saying, well, we don't really know whether the mu is going to be less than now or more than. Potentially this machine has started to overfill our flour bags or underfill. We don't know. We're doing a test to see what's the case. And the statistician will lay that out from the start. They will have an idea in their mind that they want to check. And that's the type of test that they will start off with. Now, if they have an idea that the bags of flour are being underfilled, then they will do a one-tailed test. If the statistician has an idea, has no idea, but just wants to check the accuracy of this test, or check the accuracy of the machine which is filling the flour bags, for example, then we're going to be doing a two-tailed test. Now, for a normal distribution, this is pretty straightforward, because we're just going to split the 5% between two of the ends of our normal distribution. If we were going to test to say that the mean is greater than something or other, mu0, then we would just be looking at the 5% area at the top end of the original distribution. So if we land in this, then we can be fairly sure that the alternative hypothesis holds true. And if we land in this, under the alternative hypothesis that we are less than mu0, then we would need to be in the lower tail. Hopefully that is making some sense, but it should make some sense through the example. Okay, if you want to pause off because this is all a little bit too much and try the first example in the exercise, absolutely go for it. Otherwise, I'm going to hit into this straight away. Okay, so example 6 says the times taken by an athlete to run a circuit near his home can be modeled by a normal distribution with a mean of 15.4 minutes and a standard deviation of 0.62 minutes. The athlete's work takes him away from home for 6 months, and on his return, he is interested to see whether his average times have changed. Maybe they got better due to his different training regime. Maybe they got worse. He records his time over the first 5 days after his return and obtains the following times in minutes. Okay, so we've got 5.4, 15.5, and so on. Okay, use the p-value to perform a test at the 5% significance level to see if his average time to complete the circuit has changed. We don't know if they've improved or not. We are just checking to see whether they've changed. Now, of course, if you work out a mean for those, you will have a fair idea that they may have improved or got worse. But because the test is set up in the way in which we're just interested to know whether they've changed, then it is a two-tailed test. Okay, so that's part A, and part B, we're talking about finding the critical region for this test. Okay, so we've got two ways in which we want to do this thing. So let's just hide this stuff off for the moment. Let's do it. Let's check with that afterwards. So again, we're doing this in two ways. We're either doing a p-value, or we are finding the critical region through this thing. Okay, what have I said at the bottom there? Can be done two ways, z-test function and through the inverse normal distribution. Okay, right, so let's make this a little bit smaller here. So first of all, we can say that we have, let's change the color as well. Change that to red so that I can write over the side as well. So, okay, so we've got x bar should be normally distributed Now, because this is modeled by a normal distribution with a particular standard deviation here as well, we don't have to use the central limit theorem in order to say that this is normally distributed, because it's the mean. We know it's normally distributed because they say from the start that his times have a mean and a standard deviation which is normally distributed. So we don't need to worry about the sample size being less than 30 here, because we're told originally that this comes from a normal distribution. We weren't in the previous question. Okay, so the mean in this case is going to be the mean of these values here, and I can sneakily take that from below, which is 15.4. No, I'm wrong there. Sorry, I'm wrong there. It's not 15.4. It's 15.4 because we're testing it compared to the original distribution. Sorry, 15.4. And the standard deviation is 0.62. Now remember that your calculator takes the standard deviation, but when you see it written down like this, that you will have the variance put in there. Okay, so now we should state what H0 is and what H1 is. So H0 is that mu is equal to 15.4, and H1 is that mu is not equal to 15.4. Now, obviously, we can work that one out, and we're going to need to work that one out for later on, but it's not equal to 15.4 here. Okay, now I've made a mistake here. So you can see I've made a mistake because because this is a mean, I do need to change the variance to 0.62 squared divided by the size of our sample in this case. Let's make that full screen. Take that back. And so that's going to be divided by here. 1 second. Come on to a different function. So divided by, in this case, divided by, I'm all wrong here, divided by 5, because there's 5 bits of information, I think, right? What we got here. Change the setting slightly. So divided by 5, yeah. So this is divided by 5. Remember that the standard deviation is going to be 0.62 divided by the square root of 5. Okay, so use the p-value to perform a test at the 5% significance. Now, at this stage, I would draw the graph down. I would draw the original null hypothesis graph down. So here's the 15.4, and we've got standard deviation, which we can work out from the variance, square root of that. But we're looking here then to find out whether this value, the mean that's taken from here, so whatever x bar is in this case, so our value from a particular value, so we can use lowercase x bar from the sample mean in this case. So what is that value? In fact, let's just cheat here for a moment. Okay, so now what are we getting at? I think we're going to actually have to work that one out. Okay, so we're getting, bear with me, so we've got 15.4 plus 15.5 plus 14.9 plus 15.2 plus 15.1. I'm entering, so it's 76.1, and I'm going to divide that by 5. It's giving me 15.22. Okay, so I'm getting out here 15.22. So the p-value in this case is going to be the area trapped here, but also the area trapped on the other side. So it's about being that distance away, same distance away from 15.4 on the other side as well. So it's basically asking what's the probability of x bar being 0.18 away from the mean. That's what we're asking on this side. So we'll also need to find out the probability of being the same distance away on the other side and adding those two things together. So I'm getting 15.58 on that side. So now I need to work out the area which is trapped in here and in here. And that's my p-value. Now, I've got a suspicion that they're going to ask, they're going to suggest that you can do this straight away on your GDC, of course, but by doing a Z test in this case. So we can do this via a Z test, and we'll show that version in a moment as well. But this method, which I'm going through here, is completely valid. Okay, so what do we want? We want the probability that X bar is less than or equal to, if you want, it makes no difference in this case because it's continuous data, 15.22 plus the probability that we're greater than this. But seeing as that's going to be the same size of probability on both sides, I can simply do 2 times this thing here. Okay, so let's get that p-value out. So I'm going to my calculator now, I'm going to Scratchpad, I'm going to menu, I'm going to probability, and I'm going to distributions, and I'm going to do normal CDF. Normal CDF, I want to go up to 15.22, and I've got mu is 15.4, and I've got sigma is equal to 0.62 divided by the square root of 5. Okay, square root of 5 there, because obviously we were given the variance up here. This was the variance, okay? So I'm going to press OK on this one. I'm getting out the value of, I'm getting out the value here of 0.258. Oh yeah, because I haven't doubled it. Times that by 2, times my answer by 2. So let's do times by 2, and we're getting there 0.51622 something or other. And there we go, we can see that verifies with this method here using the p-value. Okay, let's have a look at how they do that then in the book, because I think they're doing that for a t-test on this one as well. So let's just go down. Let's open that one up on here. Let's go across to example 6. Let's just check that one. I'm not going to do it myself on this one. Let's just talk through it. So you can see in this case that they've put this information actually into a table. And I suppose the reason why they're doing that is because there's 2 options. You can either use a stats method or a data method. When it comes to choosing your input method, if you choose data, then you'll have to have data from a table. So if you want to use the p-value test straight from your calculator instead of drawing out and figuring it out from your graph, you're going to need to put that information into your spreadsheet. And then when it comes to doing the test, you can do this from the spreadsheet. You can do it from there, menu, stats, stat test, Z test. In this case, use a data method of entry, and you can use the null hypothesis, mu is equal to 15.4. Sigma is 0.62. Again, they're doing the central limit theorem and the X bar distribution for you because you're entering the number of pieces of information for them. So you've essentially given them n because there were 5 entries into that list. And then list, it says time. Not sure why they're choosing time there. They've got frequency, which is 1. And the null hypothesis is a 2-tailed test. Pressing enter, and we're getting out 0.516. Okay, the reason why they're saying time is because that was the label for A. Now, if you want to here, if you didn't label it as A, as time, if you didn't rename this thing, you could have just put that in as A and square brackets. So that would have been fine to come up with that as well. Okay, so obviously this is a quicker method, and you can go with this if you want, but this does not help you to get your critical value. Okay, and that's the next part. So if you understand the way in which I did part A here, then you will understand how to get part B quite quickly as well. But there is a slightly quicker way of doing this if you use the calculator method as well. Okay, so let's look at part B. So part B is saying here we go, let's just change our color of pen. So part B is saying find the critical region for this test. So the critical region is now going to be to say, well, we're looking for the region where we're trapping 5% here and here. So we're looking for those critical values which we don't want to have gone past if we're still going to accept H0. Now, if we find out that this value is in the critical region, then we can say that the alternative hypothesis is accepted. Okay, so previously, 5.22 obviously gave us a probability of 0.516, so 52%. 52% was way higher than 5%. So obviously we're going to accept H0. We're going to accept that this athlete's times have not significantly changed. Okay, so let's just rub a little bit out here. So what we're looking for now is that critical region. So let's take this back. So we're now looking for this value here. Let's come up with this value. Let's call it A. That's what they call it as well. So this is no longer 15.22. This is A. And we're now saying we're going to see if this lands into one of these sections here or here. We're going to need to find A. We're also going to need to find this value as well, because we could either be before this or we could be after this. But once you find this one, it's easy to find this one, of course, because it's the same distance on the other side of mu. Okay, so we've got here that we need the probability that X is less than or equal to A, or just less than A, because it's continuous. It's got to be equal to 2.5%. 0.025. Now you can see that they're doing the inverse normal distribution here, if you can possibly see that at all. They're going to say, well, how do we work this out? Well, we need to go backwards here. We're not saying what's the probability. We know what the probability is. The probability is given. We want to know the value that gives that probability. So we're talking about the inverse normal distribution in this case. Okay, so we're going to go to our calculator, and again we're going to go to Scratchpad and probability. So menu, probability, distributions, and we're going to go to inverse normal distribution. The area we want to trap is 0.05. Mu is equal to 15.4, and sigma in this case is equal to 0.62 divided by the square root of 5. Okay, remember again, because it's a sample mean, we need to divide by the square root of n for our standard deviation. Okay, so that's giving us out 14 point. That's giving us A is equal to 14.94, so on. Okay, so we potentially need to find this value as well, but actually because this is lower than 15.4, we can see that this is definitely not going to be in the region above 15.4. But we now do need to consider the 15.22. We're going to need to work that value out and see whether or not how that compares to this critical value. Because it is not lower than this critical value, we can see that we would not accept the alternative hypothesis. Now, by the way, you might want to call this A1, you might want to call this A2, and that's quite easy to find as well. It's just not necessary to find in this question. Clearly, that's 15.4, take away this, and then added on to 15.4. So it's that difference there added on to 15.4. Or alternatively, you can do another inverse normal distribution with this total area being 0.95, not 95, 975. Check that I did that right. Oh, I did that wrong. Sorry. Inverse normal distribution. Let me control copy this one. Control paste that one. That's not correct. I needed to put in 0.025 there. Okay, which gave me not this value here, but it gave me a slightly smaller value here. It gave me 856, something or other. Okay, so again we can see that this again is still way within this region here, and this is our A1, our critical value here. Okay, let's just check what they do as well, and then we are done with this. Let's clear the annotations. Let's check this for part B. So again, they've said to the examiner, we're doing an inverse normal distribution for part B. They've drawn a sketch of the graph as well. And they've said, well, here's A, here's B. So they found actually both of these, A and B. In fact, I think that it doesn't really matter because X bar, when you found it, would need to be, the fact that we know that it's less than the mean in the middle means that we don't need to work out the one on the other side. But actually the question does say find the critical region. It doesn't actually say perform the test. So if you needed to perform the test, you'd need X bar from the sample mean. Okay, but so the critical region is both less than A and it's also greater than B. So again, there we go. Just as I did, the inverse normal distribution was 0.025, 15.4, and 0.62 divided by the square root of 5 as the standard deviation. It gives us 4.86. They've done the same thing again with 0.975, but again, likewise, you could add this distance onto the mean to get the answer for B there as well. So critical region is X bar is less than this or X bar is greater than this for us to accept the alternative hypothesis. In our case, it was 15.22. So we were clearly within the acceptance region of the null hypothesis, or in other words, the non-rejection of the null hypothesis. Okay, guys, I've talked myself out on that one. Thanks for bearing with. And we've got 14E to get on with next. And beyond 14E, you have the t-test. So the t-test is going to require you to make an unbiased estimator for the population variance. Okay, right, thanks for listening.